So today's lecture is about the functional analysis. Under that, I will be teaching you all the definition of equivalent norms and one theorem. Okay, this theorem I will be teaching. Okay, so let me start with these two things. First, I will go with the definition and then I will go with the theorem. Okay, so let me see the statement of equivalent norms first. Now, what is an equivalent norms? Let X be a linear space. What is my X over here? Let it be linear space. And let this and this be the two norms on X. Now this is norm 1 and norm 2. Be two norms on X. And then the two norms, these two norms are said to be equivalent. Now when these two norms are said to be equivalent on X? If the induced equivalent matrices on X and is denoted by this, norm 1 is equivalent to norm 2. Okay, so this definition, please learn it because we need this definition in the proofs, in the one of the theorem which I will be proving right now. So next, this theorem is very important. Let X be a linear space. Norm 1 and norm 2 be two norms defined on X, and these norms are equivalent if and only if they exist constant small m capital M such that small m into norm of x1 is less than or equal to norm of x2 less than or equal to m norm of x1. Okay, outside the norm you'll have to put 1, 2, whatever it is. Now this is for all x belonging to x. Let us start with the proof. Now this is if and only if statement. So we have to prove the converse part as well. Right? So let us start with the first part. So it says what? Let two norms be. Okay, these two norms defined on x and these norms are equivalent. Right? So it should be induced. Right? For that, let the two norms be induced by x1 and x2. So here what is my x1 is equal to x comma norm of 1 and x2 is equal to norm of, x2 is equal to x comma norm 2. Here x comma norm 1 and x2 is equal to x comma norm 2. Here x1, okay. So I'll turn the page. You all can copy down, okay. And please understand how I'm explaining you all or I'm telling you all how to do it, how to go to it, okay. Let t from x1 to x2 be an operator such that t of x is equal to x, then t inverse goes from x2 to x1. It is just other way around, okay. Here is an operator such that t inverse of x is equal to x. If you put this t here, what it will become? T inverse of x, right, which is nothing but x. So learn like this way. Therefore, t and t inverse are continuous and bounded. Once if you see it is continuous and bounded, you have to bring the definition of it, which says that if it is continuous and bounded, that means therefore there exists m greater than 0, capital M greater than 0, such that norm of t of x2 is less than or equal to m norm of x1 for all x belonging to x. That is, what is my t of x over here? T of x is equal to x. So that is, instead of t of x I have put x. Okay, norm of x2 is less than or equal to m into norm of x1 and take it as 1. Okay, by boundedness of t inverse, okay, there exists a constant, meaning there exists k greater than 0 such that norm of t inverse of x1 is less than or equal to k norm of x2 for all x belonging to x. Now what is t inverse of x? T inverse of x is equal to x. So which I have put here, less than or equal to k into norm of x2 for all x belonging to x. Then put k is equal to 1 upon m. So plug it wherever there is k, 1 upon m. Norm of x1 is less than or equal to 1 upon m. Norm of x2 for all x belonging to x. So what I have done over here, I said, yeah, this 1 upon m instead of this k I have put, okay. Now m into norm of this m, I have taken it this side, okay. This m I have taken it here. M into norm of x1 is less than or equal to norm of x2 because m I have taken it at the other side for all x belonging to x, and consider this has 2. Now from 1 and 2, from this 1 and this 2, what I am going to get is m norm of x1, m norm of x1. Now where is my m norm of x1 is less than or equal to norm of x2. M norm of x1 is less than or equal to norm of x2. Now norm of x2 is less than or equal to m norm of x1. Where it is? Norm of x2 is less than or equal to m norm of x1. So from 1 and 2 we got this, right? M norm of x1. Norm of x2 is less than or equal to m norm of x1. So this we got it from. Now taking this, we have proved this, right? Now I have to take these and have to prove that the norms are equivalent. Okay, the other way around, converse part. Let us do it. Converse is what? Now take whatever you got. Now to m norm of x1 is less than or equal to norm of x2 is less than or equal to m norm of x1. Now to prove that the norms are equivalent, now we have to prove that the norms are equivalent, right? What we are going to do is take norm of x2 is less than or equal to norm of x1. Norm of x2 is less than or equal to norm of x2, no? Let us take the first part, okay? Norm of x2 is less than or equal to m of norm of x1. Now what does this implies? This implies that norm of x2, t of x2, no? See, from here I will get this norm of x2 is less than or equal to m norm of x1. Sorry, this I have made a small mistake right here. This is norm of this inside x only, okay? 1 I have removed from here, so this 1 you see only here, okay? Now this implies norm of t of x2 is less than or equal to m norm of x1. Now from where it is? From 1 I have taken, right? From this part. Now this implies this. And what about the second part of it? Norm of x1 is less than or equal to this. It is from here. This part, okay? From norm of x1 less than or equal to 1 upon m norm of x2 implies what? It implies t inverse of x is t inverse of what it implies? T inverse of x of 1 is less than or equal to 1 upon m norm of x2. Therefore, t and t inverse are continuous and bounded. So, I can say my t and t inverse are continuous and bounded, okay? This part I have understood, right? Next, I'll turn the page. Therefore, any open ball of x2 contains an open ball of x1, and any open ball of x1 contains an open ball of x2 implies norm 1 and norm 2 are equivalent. So here we are done with today's lecture. In the next lecture I will be proving more theorems and more proofs, okay?